them red giants. But the one thing you got to realize is that the rate of burn is actually related to the cube of the mass. So these guys, even though they're big and they have more fuel, these guys are brief. Okay, they don't live very long because they burn their fuel so much faster. Okay, they burn it so much faster, right? So they're burning up their fuel. These guys burn so slowly and they're so dim, right? You know that it just seems they actually burn a long, long time, right? So these guys are durable. Remember, they're red, and they're also diminutive. Red, How do you spell diminutive? Diminutive. Is that right?
Yes.
All right, there we go. I almost changed my mnemonic device for that. Right. Right. So here's the HR diagram in terms H&R block diagram in terms of time. Right. So 0.01 billion years, is that 10 million years? That's amazingly brief in terms of star life. Right. 0.1 billion years, a billion years, 10 billion years. So our sun is here just a little bit beyond that, like 13, I think maybe. Right. 15 billion years for our sun. 100, right? 500 billion years. The universe is only 13.7 billion years. So kids always say, well, how do they know? If it's right? We can divide. We know how much fuel it's got, how fast it's burning it, and we can divide, right? And you can figure out, right? It's an extrapolation, but there it is. This is the size of them, right? So as you go up here in the HR diagram, they just get bigger and bigger, right? And then this is the far end of it. There's an upper limit to the size of stars. And the reason is that because the rate of burn depends on the cube of the mass. At some point, the explosion is going to outstrip gravity no matter what. Gravity does not increase with the cube, but the explosion does, right? And so this is Eta Carinae. As soon as they got the Hubble online, like shortly thereafter, somebody had been looking at the brightness of the star, and it was like the stock market. It was like, yeah, it was like, what is this star doing? So they took a picture of it with the Hubble, and basically what it's doing is it's exploding, and then it simmers down for a while, then it collapses, and it's got too much stuff, and it explodes, and it overcomes gravity, and then it sort of sits there for a while, and then it collapses and explodes. Kind of like this couple that had the room next door to us in Newburgh. When we stayed in a hotel, right? All night long they would fight, but they'd fight like 5 minutes apart or 21 minutes apart or, an hour and a half about, damn it, Dwayne! You're like, oh, not again, I don't know. We called them damn it, Dwayne and wife, right? So the death of a star, right? Okay. This is that notion of the whole core, right? The core is going to collapse. Right? This core is going to collapse. It's going to turn into a red giant, right? And then that's the diagram here, right? So if you go out here, it's like boom, it goes out here. It gets simultaneously cooler but brighter. How do you do that? Bigger. You get bigger. Size is the one thing you can infer, right? So these things are just super giant. Red giants are just super giants, right? Cools down, expands, right? It blows a whole lot. It blows like 7/8 of its mass or 3/4 of its mass into space. And this will be handy later, right? And then, here's this stunning image. This is an artist's rendition of the Earth. The sun is a red giant gobbling up Jupiter, right? There it is, right? And then I used to be really worried about this. Like I complained to my parents, I go, geez, it's going to eat Earth and then we're all going to die. And my parents explained to me in the nicest way possible that I'd be dead long before then. Right? Which I didn't like that either. It's like, gee, that's no fun, right? Okay. Now, you've got this helium core. The explosion that puffs it up to the red giant is actually another hydrogen explosion, right? But when it puffs out like that, what it's going to do, if it's got enough mass, is it's actually going to do helium fusion, right? Notice that helium turns into things like carbon, right? And supergiant stars can be making these things. In fact, really, really big ones can just make iron right away. Okay? Iron is sort of like the cinder of nuclear reactions. You can't split it and get energy, and you can't stick iron together with anything and get energy. Right? So things heavier than iron, you can split and you can get energy doing that. That's like the bomb we dropped on Hiroshima. Right? Things lighter than iron, you can add them together, you can fuse them and get energy out of them. But iron is sort of where we stop, right? Okay, now carbon, we're fusing helium, right? We're fusing helium. We've done this, right? We've gone, blah, right, or something like that, right? Okay, then we contract. We're now fusing helium. Well, helium is making carbon. Where does the carbon go? Carbon's going to the middle of the star. This is all going to happen again, isn't it? Right? We are not hot enough to fuse carbon. Carbon is falling into this core of the star. As that gets bigger and bigger, doesn't your helium fusion die down? Yeah, but gravity never quits crushing, does it? No, so it's going to collapse again, right? Okay, this time it's not quite as spectacular, right? So here it is. It's heating up and contracting. That's this little branch here. Do you have this diagram in your... Yeah, so label it with this thing, right? So here is, label this one, hydrogen fusion stops. Stops, right? And you could write the helium core is too big. Right? Okay, hydrogen fusion stops, the helium core is too big. Right? Okay, this is the red giant. Right, we call it a red giant though when it's on its way out there and even on its way back, right? Here is, it's heating up and contracting, so this is helium fusion. How do we know it's heating up? How do we know it's contracting? We know both those things. Look at the trajectory. It's going left, isn't it? So that's hotter, isn't it? Yeah, right? And then it's getting not as bright. If you get hotter and not as bright, what do you have to be doing? You have to be getting smaller, right? Now, by the way, how we know it does all this stuff, I'll show you in a sec, right? Okay, but here, so this thing is contracting, it's heating up, contracting, right? Okay, and then, okay, this is another expansion. We are getting colder but brighter, right? Again, we're getting colder and brighter. That's another expansion. That is the collapse of the carbon core, right? So the same thing happens. You could draw a star here, and it's helium fusing, in the center is carbon, right? This carbon core is eventually going to collapse because the star cools down because the carbon core is too big. Same process that happened here, right? Only this was helium, hydrogen on the outside, helium in the middle, right? This one's carbon in the center and, you know, some hydrogen and helium out here, right? Okay, this thing's going to contract, right? And carbon, of course, is going to make things... Right, so there's cooling down, expanding. This is the explosion, right? It's going to eventually turn into a white dwarf, right? So carbon is making things like magnesium and silicon, right? Even if you've got a hot enough big star, you can make things as heavy as iron or nickel. But you can't go beyond that with fusion, right? Because of something called binding energy. So let's take a look at this thing, right? If you look at this graph, this is not energy you have. This is actually energy you need to separate the atom into all its pieces, right? If you go this way from here to here, right, you're actually releasing energy. So hydrogen to helium releases a tremendous amount of energy, right? The bomb that we dropped on Hiroshima went from elements like this to elements like this. See how much energy that is? Is that a lot? No, not really very much, right? So fission bombs, things that create fissures, that split atoms apart, are going from here to here. Not a huge change. Still tremendous compared to chemical reactions, right? Per nucleon, it's like 200 million electron volts of energy. In a chemical reaction, it might be 10 electron volts of energy, right? A super energetic thing like nitroglycerin, 10 or 10-ish? Yeah, on the order of 10. These reactions are 200 million electron volts of energy per reaction, right? And that's when Einstein discovered this, and he discovered that equivalence, right? That's when they realized, gee, this bomb's really going to hurt, right? Later, in the 50s, they developed the hydrogen bomb. Hydrogen bombs go from here to here, right? The yield of fission bombs is in kilotons of TNT, thousands of tons. 20 kilotons is what we dropped on Hiroshima, right? The yield of hydrogen bombs is in megatons. Yeah? Those are the things that, like, one of them destroys an entire city, right? Now, if you look at this, right in the middle there, that's iron, right there, okay? Okay, iron and nickel are right there. You can't do anything with those. You can't split them. If you did, it would require